Welcome. We have a team of the Technical University of Darmstadt here. I'm really happy to welcome you. You did a technical noise study on behalf of SENA. You elaborated that. SENA is the Competence Center Climate and Noise Protection in the air traffic. If you don't know SENA, that's the name. You had literature research, you participated in conferences, so you really developed a lot of know-how and processed it. And that's really great because we will be offered an overview about all that subject, and later we can talk to experts in practice and see how it has been implemented. That's the presentation. We have Mr. Louis Reitter here, Master of Science, scientific employee in the area of flow science and aerodynamics. His research focus is the study of ice crystal icing with engines, aircraft engines. Then Florian Goertz, also Master of Science, scientific employee in gas turbine, aviation and aerospace drives. He deals with the numeric turbine simulation of the combustion chamber turbine interaction. And Pascal Menner, Master of Science, scientific employee at the Institute for Flight Systems, Regulation Technology, research focus, integration of a ground station for flight missions with reduced cockpit crew. So you brought all your expertise with you. You did that study together, and you have divided the parts. Everyone will have their own part. You have a bit more time, so it takes a bit longer, this presentation. It's more comprehensive. So, yeah, let us start. You are wired, and so you can just click further, and we are looking forward to your presentation.
Good.
Okay, perfect. You can hear me okay. And thank you very much for the warm words of welcome. Here you can see our pictures once again. And let me introduce the heads of the department, Professor Hussong, Professor Reitter, Professor Skipper. And what can you expect in the next 45 minutes from us? In 2020, the SENA, the Competence Center Climate and Noise Protection in Air Transport, got in touch with TU Darmstadt, and SENA was established by the Hessen state government, and asked us to identify some noise abatement technologies on a plane. And this is exactly what we did. So we tried to make a list of all the noise reducing technologies of the past 30 years. We analyzed the impact on noise abatement, and we also made a forecast. So what kind of technologies are in the pipeline at the moment? What kind of benefits can we expect? And can we quantify that benefit? And then if you take a look at the right-hand side, we also tried to cover basic research. So what kind of research is there, and what is the state of research? But this is not what we're going to cover today in our presentation. But if you're interested, please download our report on the SENA homepage. You will get much more information. The data, this is what we already mentioned, come from a broad literature research. We all come from the university. We know how to read a paper and how to analyze it. So this is where most of the data come from. And in order to assess all these comprehensive documents, we got in touch with industry, Rolls-Royce, Lufthansa Technik, Boeing, and we also got in touch with the universities who wrote, for example, and the institutes who wrote these reports like NASA or DLR. But before we give you an overview, we would like to share these information with you, just to be on the same page. How can sound or noise be quantified? If you take a look at the left-hand side, you can see piano keys, and I can press one of these keys, and then you will get a sound with a certain frequency. And depending on whether I push it harder or lighter, I can get an amplitude, and this is then giving me the sound pressure, the amplitude. And if we talk about noise, and especially about aircraft noise, then it's not a tonal noise source, It's rather a broadband noise, as you see it in the center. We have different frequencies with different impacts, and you can see it very nicely here in the middle. Now, a first step which was made in quantifying noise was taking the characteristics of human hearing into account. This is representing by the green line, the hearing threshold. Here we're talking about 20 hertz to 20 kilohertz. This is quite a broad range, and you might know it from yourself that you don't hear the outer ranges, but when it comes to 3000, 4000 hertz, this is the optimal hearing. And exactly these characteristics are being weighed, and then you will get the noise impact. When it comes to aviation noise, it's also time which is taken into account, which means we are differentiating between constant noises or individual warning sounds, one-off sounds. And this is also taken into account, and this brings us to the effective sound noise. And this is also being quantified, and we try to use all the technologies and bring it down to the EPNDB value in order to make it comparable. And this brings us to the main part of our presentation. We're going to present some noise abatement technologies. Here you can see a plane in a standard configuration, and even if it is idle here, the engine is still the dominant source for noise. And then we're going to move on to the landing gear, and then we move on to the green area, the flaps, the slats, the wings. And finally, we're going to bring all these parts together, causing noise, and give you information about what is possible to do against the noise. Let me start with the engine. Before I come to the measures in noise abatement, I would like to talk about the noise sources. What is dominant here? You can see, for example, on that slide, a fan and a compressor. This is usual for each and every plane we know. And if you take a closer look, you will see the fan once again, then the compressor, which comes next. Then we have the chamber and then the turbine. And behind the turbine, you have then the jet. And looking at the engine, you will see that noise is being caused everywhere. You have the rotors, you have the fan, the compressor. This is where you will get tonal noise caused by the interaction coming from the cold secondary flow, the hot primary flow, and when it comes to the jet, you will get a broadband noise. This differentiation is very important because a tonal noise is being heard at a different frequency, and a broadband noise has another frequency. If you take a look at the top right-hand corner on that slide, you can see where most of the noise comes from. You will see that the engine noise is dominated by the fan and the turbine and the radiation noise. And the combustion noise, for example, and the turbine noise are a little bit lower than the fan and the engine noise as such. So this is where you can see most of the effects if you do something against the fan or the engine noise. What has been done so far, noise reduction to date, since we had, for example, jet engines in civil aviation? They started in the 1960s. Then you will see that the first jet engines were 30 decibels louder. So it is a lot of noise, and the noise was reduced between the former jet engines and the ones we're using today. And there are two reasons, two blocks. Engines have been further developed since the 60s. We have a reduction of noise generated And to be fair, this kind of further development was also made in order to use to lower fuel consumption. However, this also went hand in hand with the noise which was generated. If you use less fuel, you will have less noise produced. Then we can see that we have an attenuation of the generated noise by, for example, acoustic linings. This is how we're dampening the generated noise as well. Let me carry on with a very important factor for reducing noise. It is increasing the bypass ratio. On the left-hand side, you can see a single jet engine, and it works like that. You have a little amount of air flowing into the jet engine, then it's being densened, it is being burned in the engine, and this kind of bypass ratio is being increased to a higher speed. Higher speed means more noise, and this is in the amount of the factor 8. This is multiplied by 8. So if you increase the bypass ratio, then you will have less noise. What was done, and this brings us to the picture on the bottom left, a different kind of bypass engine was used. You're not using the core engine, but most of the air is bypassing the engine. And this is how you have much more airflow in order to have exactly the same draft. You have lower speeds in the jet, in the stream, and this is then leading to a massive noise reduction. This was also done in order to reduce fuel consumption dramatically. However, it also shows us the limits of the development, and one limit is given by having more masses in the turbine. The turbines need to be bigger, and bigger turbines mean more weight. Then you have more drag, and at the same time you need more space, more room to assemble these kind of engines. You need a longer fuselage, and this is why optimizing fuel consumption has its natural limits. It does not make sense to make it bigger and bigger. So this is why this kind of development is reaching its natural limits. However, the noise from the engine was reduced dramatically by that increase of the bypass ratio. So the fan noise and the engine noise are comparable now. And then here you can see further measures in noise reducing. Here you can see, for example, the nozzles which were modified. The jet noise is caused by a mix of a high-speed jet and, of course, the environment, the air. And then we have smaller and bigger turbulences, and if we have smaller turbulences, it is a high-frequency noise, and then if we have smaller turbulences, it is a low-frequency noise. And you might know it, the bass, for example, if you are attending a concert, a bass is always very loud, and the higher frequencies are never as loud as a bass, for example. So a mixing of turbulences is something which is key. So we try to mix, for example, the high frequency and the low frequency turbulences, and this is why chevron nozzles were introduced. And here we have the so-called forced mixing, which makes, or the compulsory mixers, which are accelerating the mixing by splitting the main jet into the many small jets. So I talked about some aspects in noise reduction when it comes to engines, fans, when it comes to nozzles. But what else is possible? What is reducing noise dramatically? Well, noise can be reduced by acoustic linings. You can see them, for example, here on the left-hand side. This is a sandwich construction, a sandwich design. Here we have, for example, one layer and then the honeycomb structure which comes on top. And you can see that we're damping the frequencies, which means the sound is entering this kind of Helmholtz resonator, as it is called, and will have something like an attenuation of the individual frequencies. We have multiple layers which can be stacked, and they're damping then the frequencies. However, only individual frequencies can be dampened here, which means tonal sound can be reduced, no broadband sound can be dampened. However, it is being used, for example, to reduce the fan noise. You can see it in the center. Everything which is highlighted in red is being lined with these kind of acoustic linings. So it is being used to reduce dramatically the tonal fan noise. And the state of the noise reduction is, for example, a reduction of the noise by up to 12 EPN/dB. And without the acoustic linings, the fans would be much, much louder, twice as loud to be precise. However, these acoustic linings can only be used to mitigate tonal sound, nothing when it comes to broadband noise. And in some situations, the acoustic linings helped very much against tonal noise, but the broadband noise which exists in fans is not being treated. And in order to make sure that a further noise reduction can be reached, acoustic linings are needed to reduce broadband noise as well. And you can see it on the right-hand side, and I mentioned it at the beginning. The engines are getting bigger, and of course, people try to reduce weight wherever they can. And here we have, for example, the engine nacelle, where we can add some acoustic linings, but to reduce the weight, they try to keep the nacelle as short as possible. But to keep that system, for example, efficiently, you need to have an inlet which is also shortened and a nacelle which is then longer. And what is being done? What kind of research activities are there? You can see it on the bottom left-hand side. Over-tip rotor liners are being used on the rotor tips. And of course, this is not that trivial, not that easy, because we have, of course, the interaction with the rotor as such, which has to be taken into account as it is a crucial safety aspect we see here. So linings being used there is something which still needs to be further examined, and research is being done in this area. And then on the right-hand side, you can see other options like the broadband liner, for example. So flexible materials are being used to dampen through material properties. Flexible materials which can reduce the noise. Or actuators are being used, for example, to lower the frequency range. Further measures to reduce, for example, fan noise are active measures. And the principle is similar to what you might know from noise-cancelling headsets, which means you are reducing sound by countersound. And if you think of noise-cancelling headsets, then you're using, for example, error microphones and loudspeakers, creating, for example, some countersound. But we have learned that there is not much of a benefit compared to acoustic lining, which means the noise reduction is not that dramatic. If we want to see a better effect here or a higher effect here, then DLR tries to use, for example, compressed air injection between rotor and stator. Other measures which are being analyzed and researched right now is, for example, treating the blade leading edges, which means using wavy or jagged edges. But this is not very much advanced at the moment, as there are other challenges to face when it comes to stiffness, aerodynamics. So this is a massive change, for example, to amend the blade leading edges to make them wavy or porous. So it will still be in the focus of research, and it will take some time until we can see some finished products which will be offered to the market. This brings me to the end of my part when it comes to engine noise. I tried to present some noise cancelling or noise reduction possibilities, adjusting the engine parameters, increasing the bypass ratio, then acoustic lining to dampen the sound. And there is a lot of research being done on active countersound measures. And finally, I would like to make a brief forecast of further engine noise measures. Well, we expect only small improvements in the near future. How comes? Well, we've already reached a lot by reducing the jet noise, and now people know that jet noise and engine noise are comparable. So there are two sources which need to be tackled at the same time. So the task is getting more complex. And in some configurations, like in the landing approach, for example, these two components are not that much louder than the original engine noise itself. And this is why more and more components need to be tackled in order to efficiently reduce noise. And this is why small steps can be expected in the future when it comes to reducing engine noise. We assume that a big step can only be made if we have a noise-optimized aircraft design. This might lead to a technical leap forward.
Applaus.
Okay, I will continue with the landing gear. As mentioned at the beginning, especially in the approach, the landing gear has a very dominant significance, just as the engine. Before I talk about the measures, I would like to start with an interesting fact. Maybe if you go down a bit, the lower picture there is by NASA. With overflight measurements, they have found that the nose under the cockpit, although it's much smaller and slender, produces more noise than the larger main landing gear. And a proportional correlation is noise is proportional to the flow speed with a potency V to a factor of 6 to a factor of 8, depending on the source. So you can reduce noise by reducing flow speed. That's a fact that we need to consider again and again. And with the main landing gear that is under the wings, and the wings, they create uplift, and the flow at the lower side is slowed down, and this slowing down is enough so that the main landing gear is not the dominant source of noise. So that you see how it looks like. I brought one with me. It's relatively complex. Some larger ones like the strut, the braking system, the tires, the wheels. So I think you see it quite nicely. A lot of small cables, hydraulic lines for the brakes. And all together that leads to a broadband noise 2000 to 3000 hertz. That's more or less when the human ear is most sensitive. But I come back to that. Now, how is noise generated? We have a flow situation from the left. It flows around a component, and after that, behind that, there is a turbulence wake, and this is what we perceive as noise. It's pressure fluctuation. And you can see in general terms, large components produce big turbulences, the low frequencies, smaller ones produce smaller vortexes, the lower frequencies, and this is how we have the different frequencies. And what we also have, and maybe in the upper area you don't see it that well, that's the shaft. That produces its own characteristics of noise. And well, what possibilities do we have, especially with the components that you see here? With the landing gear, you can only optimize them by lining them, by cladding them. You have fixed and porous claddings or linings, and with the fixed claddings, it's the objective to shield critical component. That is, the flow goes around, is deflected around. There's a big disadvantage. If you deflect flow, you accelerate it. Always. And I said it before, it's noise proportional to speed. And when I have the deflection hitting another component with a higher speed, it might happen that a cladding might generate noise at a different place and partially even louder. And therefore, fixed claddings are not very good as a retrofitting, but rather should be considered for each and every aircraft type, landing gear, what have you, and have to be calculated, of course. And then it becomes heavier, it costs more energy. So components need to be maintained, brakes want to be ventilated. All these are negative impacts, so that fixed claddings are not that appropriate any longer. Since the 2000s, there have been quite a few studies. These are the latest ones. The DLR Braunschweig with the ATRA, Project Low Noise, and in the middle, Echo demonstrator of Boeing. That's where they tried it, and several areas marked in orange were covered. And I think the results have been published now. When the report was written, they had not been published yet, but we assume that a noise reduction potential for the total aircraft of about half an EPND can be achieved. This is not very much. In comparison to that right-hand side, porous claddings or linings, hopefully you can see it well. The cladding in the front area has two black squares. These are many little boreholes which allow the flow to penetrate the component. With that, we slow down the flow, and slower flow, less noise. And there is a second advantage. With the size of the holes, we can determine in what frequencies noise is generated. And here it's important to know the high frequencies, 3,000-4,000 hertz, are relatively dampened by atmosphere. After several hundred meters, you won't perceive them, whilst the lower frequencies can cover long distances. You know that the neighbor has music too loud, you hear the buzz, but not really the music. And that's precisely the effect that they want to use here with the porous cladding. And right-hand side, that's a NASA experiment, 2016, and that was minus 1.4 EPNdB. You have to put that in relative terms. It was a research project, so the landing gear could not be retracted. So if you design it for real aircraft traffic, you have to change it. But definitely you can reduce more noise than with the fixed claddings. The second part of the landing gear producing noise is the landing gear shaft. You see it here, less than 1000 hertz. That's the lower frequencies that you can perceive over long distances. And they are produced. The flow comes from the left, penetrates the shaft. The shaft acts like a resonance body, like a bass box, and radiates to the front. So that's noise you perceive already before the aircraft has passed by. And for that, there are different approaches. The most logical is the video that you see here. The real shaft with start and landing is not fully opened, but there is a flap mechanism. So while starting and landing, a big part of this surface is covered. There are aerodynamic reasons for that, but there are also positive effects when it comes to noise. Disadvantage, mechanically, there's always a little gap open. And here, that's the picture in the middle. NASA looked into different technologies in order to optimize this remaining gap. The best technology was a combination of a front edge toothing to optimize the flow in combination with a noise-absorbing foam at the lower edge that should stop resorbation. This is a simple retrofitting measure with 0.5 EPN dB noise reduction potential. Just to remember, the claddings on the left-hand side were also 0.5 EPN dB, and they were much more difficult to design. Maybe that's a measure that you can really do and consider as retrofitting. On the right-hand side, you can see a look into the future. Here there are possibilities or theories that the flow could be deflected around the shaft with a mechanical spoiler like in the top picture, or, that's interesting, with a 90 degrees turned around airflow that deflects the flow. These are technologies that have not matured a lot, so they need to be researched more, and in the next 20 years maybe they are not available. So the video once again. There is another problem with landing gears, and I think DLR has known that for 20, 30 years. They've always considered that. These are the so-called shaft holes. So everywhere at the landing gear there are little cavities, and especially with lateral winds, if there is lateral flow, there might be tonal frequency peaks. Maybe you see that here. These are the whistling sounds that you hear. And you can eliminate them easily by just having a plastic cap on it or made of a different material, such a cap. We talked to experts and they said it's a super solution, can be easily done. And other experts said, very bad idea. Condensation water might accumulate for starting, landing. That might lead to collisions, and you don't really want to have the landing gear breaking off during start or landing. So a very difficult discussion, especially with engine manufacturer. So you could mention that as a design hint. So that shaft holes, maybe when designing the aircraft, should be considering that point. That was it already when it comes to the engine and the landing gear. So noise reduction of 1.4 EPN dB with claddings could be achieved, and 0.5 with the shaft optimization, and that's a total potential according to DLR for the landing gear. 4 EPN dB noise reduction is possible, only related to the landing gear. You have to calculate that together with the other components. The final value will be available at the end of that study, so we have to do some more work.
Ja, lassen Sie mich nun den
Let me move on with the last aspect of our presentation. It's the high lift system of a plane. And here there are different noise sources I would like to present to you. First of all, we have the noise which is being caused at edges and also in gaps. We can see some vortices, then some turbulences which are being caused, and this leads to broadband noise. And the potency of scaling is a little bit lower than the one we had with the previously presented phenomena. Now, if you take a look at the plane here, You can see the two biggest noise sources already. You can see the gaps between the front wings. You can see it highlighted in red. And then you can see a noise source coming from the flap side edges. In addition to that, there are more noise sources which can be mentioned. However, the two big ones are, as I already mentioned, the slat gap and the side edges of the flaps. If you have such a high lift system, it is important to have a low climbing speed, which means if you are interfering with that high lift system with noise abatement technologies and reduce this kind of system, you need more speed, and more speed means more noise. So you have to be very careful with the impact a certain noise reduction measure might have. Let me start with the slat slit noise. You can see it's dominating the low frequency range, and if you take a look at the left-hand side, you can see the heat map, and you can see where the noise is being generated. At the front side of the wing, here we have 800 Hertz, and the mechanisms which come into play here and which will lead to noise can be found on the right-hand side. At the end of this slat, you have this detachment bubble, which is oscillating. And then secondly, you have at the upper edge the mixing of two airflows, and they're being deflected. And if you want to reduce heat, these two phenomena need to be influenced. And this can be done with the support of three concepts. You are adding, for example, attachment parts, as my colleagues have already presented. Then you have to optimize the slat design, and you have to find an alternative HAS architecture. So let's talk about the possible attachments. Well, they have some reduction potential. However, that potential is not very high, and the technologies are not very mature. Starting on the left, for example, you can add some brushes at the edge of the slats to increase the mix of the airflow, or you're adding some slat horn triggers which are then changing, for example, the oscillating blister. However, it might also lead to higher noise. It's very ambivalent, and it is still being researched. Then porous inserts are also possible. Their impact on noise is comparable to the landing gears. So we can have, for example, a slat cover liner, which means adding some cladding or liners to the slats, or you are changing the geometry. Making the lower edge, for example, longer is also something you can do to reduce noise, as the effect of the oscillating blister is being reduced. Then we come to the next and more drastic approach. It's the optimized slat design, which means you change the slat design. It already works quite well if we take the Airbus A380 and A350. They have a new slat design where the slit is only very narrow, and this is why less noise is being produced. And if you optimize that, if you optimize the parameters, you can, for example, play with the gap width or the overlap which exists at the edge. And here we're talking about an effect of 0.5 EPN/dB. You can also choose a very long slat, which means it goes beyond the edges. Or you can also have an adaptive slat. This is what DLR has analyzed. And then you will have a flexible structure, and you need to adapt the gapped width, and this has an impact of 0.5 EPNdB. Then you can also choose alternative HAS architectures as being already used in the A380 and A350, which means you have a hinged droop nose, and this is an alternative between the attachment or the noise-optimized slat, which means we are having a rigid body movement around the pivot point, and we are impacting the edges and the geometry. And this kind of droop nose has a flexible front edge. The front edge is lowered and offers us further potential. This brings me to the next big area. It's the side edge noise in the back at the flaps. At the side edges, we can see some vortices, and they cause noise. You can see it here with 800 hertz in the center of that slide, and very locally this noise is being generated. It's broadband noise again. And if you want to reduce this kind of noise, you have to change the geometry of these side edges. That's the way you can change or have an impact on the vortex. The vortex can be increased, and that's the way you have a different impact. You are changing from higher frequencies to lower frequencies. So it's quite simple. And noise reduction is, for example, also possible by design optimization. Think of the 747 and the A340. If you compare them, you can see less flaps. The flaps are broader, wider, less edges, less complexity, which means less noise at the same time. And here, the side edge noise is already reduced, and then there are some openings which still exist at the side edges. They can be closed, they can be lined, which leads to a further noise reduction. Further modifications are also possible. For example, porous side edges, brushes, fences can be used, or you are changing, for example, the edge geometry to have a more rounded shape of an edge. So this is all being analyzed at the moment. DLR conducted an A320 low noise, and a slit was closed, porous edges were introduced, and 1 to 2 decibel of noise reduction were reached by these measures. Then there's another point I would like to mention. You can see the slits between the flaps and the main wing. If you close them, then another 2 EPNdB can be saved. And tests were conducted by NASA, and there's also a second project conducted by DLR, not as mature as the NASA test, but it's exactly the same, having the flap side edge vortex suppression, flaps with flexible transition. So, my summary and outlook here, the high lift system. You can see that slats and flaps are crucial here. Speed is crucial, and if you want to have an impact on that high lift system, you have to make sure that you take speed into account, and more speed means more noise. And 4 dB can be saved if you change the slats and the flaps, but if you take the total potential of the high lift system, you will only have 1 EPNdB of lower noise impact, so it is not the biggest impact we estimate. And this brings me back to Pascal. I would like to hand over to you. This is the last slide, promised. So we presented some measures to you, and as a summary we can say in the past noise was reduced mainly by changing the engine. It was jet noise reduction. Now, however, also other systems are taken into account. So the engine, the landing gear, the high lift system, and things like that. And we tried to give you an overview in 3 timelines. So we're talking about the last 10 years where noise reduction was achieved by the renewal of the aircraft fleet, which means old planes are being replaced by new ones. Think of the A320, which is being replaced by the A320neo, and this leads to a noise reduction of 5 EPNdB. And this means if you have 10 dB less, then it is half as loud. And 5 EPNdB means a noise reduction of 30%. So it's quite a lot. And if we look at what is lying ahead of us, we're not talking about retrofits. We need to plan completely from scratch new technologies which might be used in new aircraft. The figure you can see here comes from Braunschweig, from DLR, and they estimate a potential of approximately 2.5 EPNdB when it comes to the next generation of planes. So this is half as loud as what we know as of today. And now, if we look at what the future might hold, here we have blended wing planes where you can see a completely new design which brings to a lower engine noise. Then it is estimated to have a further noise reduction of 3 to 5 EPNdB. So this will be another improvement. So as far as noise reduction is concerned, each and every EPNdB counts, and this is why further research is so important. And this brings me to the end of my presentation. Thank you so much for bearing with us, and we wish you a successful and interesting conference.
Genau 45 Minuten.
Ja, vielen Dank. Thank you very much. The 3 of you, Mr. Goertz, Menner, and Reitter, you are not allowed to go down. We have a few questions to you. And I don't want to leave you to go to the lunch earlier. We have a generous lunch break anyways. I would like to ask the questions that have been entered in Slido. But first of all, thank you very much for the basis that you have explained. And for some, maybe it was new. Maybe we have to go back to the basic understanding of noise. On the very first slide, you distinguish between dBi, PNBD and EPDNB. And that's the first question. Can you explain the difference between dBA and EPNdB? That was the first one, you know, the keys of the piano. Maybe you can go back to the first slide. Maybe that's easier. Maybe you can show the first slide again. Maybe we would go to the annex rather. We prepared a backup slide. Show the first slide in the backup. That explains it better, as all questions were around noise, not the measures. Please go to page 48 or 46. Let's take 46. Yeah. This is a highly complex subject, and we can't really do that in that short time to really talk about everything here. But I think this shows it really nicely. If we measure noise, we can measure the amplitude and the performance, that is energy per time unit. Normally we look at the performance or the output rather. And if we explain it and illustrate it, aircraft has a certain noise output, and a second aircraft compared to it, we have double the noise. So 2 aircrafts, double per time unit, and that would be 3 decibel. Problem, if we now translate that into loudness or noise, what you perceive, 2 planes next to each other wouldn't mean double the noise level. It's only 3 dB. You know it by heart. It's 16% louder, 20, something like that. Now, if we now increase it by 10 dB, instead of 1 plane, 10 planes, that would be 10 times sound output, but you would perceive it as double the noise. So that would be the 50% noise reduction, which is according to the 10 dB. And if it says dBA, it's always related to the amplitude. Only dB, it's the noise output. There's a little square in the formula. You can put it to the front, and then you can calculate it. Thank you for the explanation. For laypersons, it's not so easy to understand everything. We asked about the difference between dBA and PNDB. You mentioned that in your first slide. dBA, that's the measured value of the amplitude. Maybe you can go to slide 3 or 4. Yeah. And there was a request to the floor in the back. Can you bring the microphone there? Maybe you can go there already. dB, that's only dBA is the amplitude, and PNDB is the perceived noise in decibel, and that's the weighing of the characteristics of the human ear or hearing. So the marginal frequencies are not so powerful, but those with 30, 40 hertz more. And this is according to the characteristics of the human hearing in order to determine this final value. There is a request to the floor in the room. Give you your name, and please do that. In Slido also you can enter your name if you rather want to do it anonymously. But you can also enter your name and we can address you directly. Bertolt Full, a question about the EPNDB. I know it also with respect to the approval data of aircrafts, and it's a total of 3 measurements. And the 30 dB you mentioned at the beginning, I think that's the total level. That is, the individual levels is down by 10 dBs. So please, could you explain the question where the EPNDB are the total and the individual level? So there are 2 different ones. Can you explain that? Any one of you? Maybe the overflight value. In principal terms, with the airplane certification, there are 3 measurement points. That's what you refer to, I assume. That is departure, overflight, and what was the third? The lateral noise. The diagram that I showed to you referred to the lateral level. That's my second slide, more or less. Or we can also answer that question tomorrow. Tomorrow we get a presentation of IASA, and there it's about noise certification, and we see a picture of all these different points where the measurement is taken and according to which all planes are certified. Can we postpone it for tomorrow? Then we have the expert from the IASA there. So we park this question. But I have another question to you. The noise level reduction, are they referred to the sound arriving on the ground? Not appropriate for EPNDB. You said the total signal. You mentioned the reduction potential for the different components, and you said for the total it's a bit less. Can you maybe explain this correlation? I didn't get it properly. You can see here, you can read that question. What would arrive at the ground in terms of noise of the total plane? And is it helpful to sort it out according to components? I mean, you cannot just add up the different component triggered noise. Well, you do it component by component to understand where you can save noise, reduce noise. There's not only a flight test where you said, I have a great idea and I have a sponsor that makes the plane available and I just fit it and then I see what it does for the whole plane. There is a whole research series before that with wind tunnel tests and simulations, and normally you only do that individually for the different components and calculate it individually. You consider only the individual component first. And once you know that you might be able to reduce X percentage of noise for that component, then you can go to the final total plane. And for the total unit, you can see what result can be achieved. And this is always in relative terms to the other sources of noise. You have a Ferrari and an electrical scooter. If you take the scooter away, you still have the Ferrari that is quite noisy. You wouldn't notice. But if you only have the scooter and take the scooter away, you see the difference. So even minor sources of noise make a certain contribution, but if you consider them individually, there is a much higher mathematical effect than in the total unit. Did that answer that question? And then there is the question, how do you measure the noise reduction for the different components? The question is, what about the test regs for the different components and how you can identify that? We get a presentation by DLR. Dr. Fischer will talk about that. You might nod if you think so. So maybe we can take up this question tomorrow again. If you want to answer right now, you're welcome. Otherwise, we can postpone it for tomorrow. Maybe I can tell you right now that the noise certification test can be shown. You fly over certain points and then you have a look at the effect. If you test individual components, of course, it's more difficult. Then you would do noise measurements in the wind tunnel and you have to extrapolate them to the potential effect if that measure was part of this overflight test, plane flying over a microphone. So that's really difficult, but it's also done in order to come to the right assessment. Maybe you can show slide 18. That's where the mouse was. Yeah, here. Pictures on the left-hand side are flight over tests. A microphone error is built up here, a whole field of microphones, and here you can measure the points where the noise is generated in the plane. So with the overfly test, you can really see precisely whether it was the front or the rear of the plane or other components that generated the noise, and you can come to very exact results. Thank you. That seems to be a subject that will stay with us throughout the conference. There's one more question in the audience. Oh no, in Slido, whether for approach situations, certifications are related. At what points are delta reached? At what point is it that noisy as assumed? Referred to the location or? Yes, the measurement points where the certification takes place. There are differences. You need to carefully read the papers, and with every paper it says in the test rec, we are a microphone error, and we've had a flight altitude of XYZ, and this is not always according to the measurement points in the certification, and therefore you have to consider the results in that light, because it always looks into the optimal situation and not as they are seen. So you really have to compare the results. And that also means whether the plane is really that noisy as it's measured, or would the population perceive it louder. And that's a point that we are going to discuss tomorrow. How actively would manufacturers participate? You contacted manufacturers, talked to them. I may say that we talked to an engine manufacturer. That's a big subject, and there is a presentation of Rolls-Royce, I think, that we'll have later on in this conference. I assume also for manufacturers it's a very important subject. Yeah. We have aircraft manufacturers, engine manufacturers. Dr. Richter will also talk about that subject from the point of view of Rolls-Royce. So there will be much more input today on this subject. Now let me see. Only fan engines were looked at. What about turboprops or the open rotor concept? Can you tell us about that? Yeah, in principal terms, our focus in our study was turbofan engines, and that's really the main part of our presentation. With turboprops or open rotor, as it was mentioned in that question, of course you have a big noise problem. I had a big focus on the acoustic linings, that the noise generated can be attenuated with linings. With the turboprop, you don't have a casing around the rotor, and therefore you can't really change the situation with the help of acoustic lining, and the same with an open rotor. That is, in terms of noise technology, that seems to be much more difficult to attenuate the noise. We have a request to the floor here. Krauskopf, City Dreieich. The uplift, the high lift system. I wanted to ask a question about that. In big distance from the airport, that is more than 20 kilometers away, in the approach, you notice that all of a sudden there is this howling, hissing noise of the aircrafts. You don't hear them for a long time, but then all of a sudden you have that noise, and that ends after a few seconds, and then it's the ordinary noise level again. Is that the point when they open the flaps or the pre-wings, or would that happen only later in the approach? Mr. Quilling nods. So obviously, for the district of Offenbach, it's also important. So these are the municipalities further away from the airport. Who wants to answer that? I can't answer it for sure. I'd say the point in time they would have been opened already when uplift comes. It could be possible that it coincides, but I don't know it for sure. Could also be the landing gear that is extended at some stage. It's the decision of the pilot when to extend it. Not all pilots want to do that at the last moment. And as soon as you activate the uplift system, the effects that you describe happen. And when we extend the landing gears, we have another effect. You can't change it. You need that for landing. But maybe in other presentations we can come back to this. All right. I think it's shortly before the lunch break. 3 minutes to go. So thank you very much for all your questions. Here in the room and also in Slido, I noted acoustic lining and cladding seems to be important. Professor Enkert will talk about that tomorrow. So you have less space, but you have to develop a better solution. How does that work? And what I learned from your presentation, originally thought there is a whole wealth of measures, retrofitting measures, and you can improve, clad something here, line something here, and then it becomes more silent. That seems not to be easy, but we are going to listen to that precisely. We look into the retrofitting measures that happened in the past where certain results were achieved and what is being done with modern types of aircrafts. You said that in modern aircrafts you do it that way anyways, and therefore some retrofitting measures are not worth it. And what will we see in the next generations of aircrafts, new types of aircrafts where you could solve that problem? And then we also talked about the eco-demonstrator of Boeing. Mr. Stoker will be asked about that later on, what happened with this and the cladding of the landing gear, whether it's worth it or not. And you also mentioned the shaft holes, which produce a very big nuisance. And maybe new types of aircrafts don't have that any longer. So these were very specific subjects. Rest assured, even if we have not answered all the questions after the first presentation, we have many more presentations to come on very special and individual subjects, only about engines, then landing gear, claddings, etc. So we go more into detail. And should you have further questions, you can also enter them in Slido during the lunch break. You can discuss with each other, and with this discussions, maybe new questions come up that you can enter, and you also have a reply function. If any one of you has an answer already, write the answer into Slido and give your names. So, 12:30, enjoy your lunch break, have interesting talks, and at 2 o'clock we meet here again.